Now we are moving to the next chapter, that is the phase control rectifiers. We will start with the definition of rectifier, and then we will see what is phase control rectifier. These things we do. First, what is a rectifier? Rectifier, it is a circuit which converts AC to DC. We have to discuss phase control rectifier. Phase control rectifier, it is a static power electronic circuit which converts the AC, fixed AC to variable DC. What is phase control rectifier? It is a static power electronic circuit which converts fixed AC to variable DC. We are discussing phase controller, meaning here we change phase angle between two parameters. Generally, phase is defined between any two waveforms. It could be voltage or current, anything. Here we change the phase angle between input supply voltage and the supply current. Generally, the input voltage is taken as reference. Vs equal to Vm into sin omega t. This is the input voltage. Now we will control the instant from which the current starts coming into the circuit. These things we will see once we go to any pulse converter, single pulse or two pulse. But here I am explaining the technique. Phase control meaning the phase angle between the input voltage and the input current is varied to get the variable DC from the fixed AC input. Now we will see simple rectifier circuit. We start with very basic rectifier circuit, that is diode based circuit. Assume input equal to Vm into sin omega t. This is diode and this is a resistor, my load. We will see how the output waveform comes. Output waveform meaning what? Our output voltage and also the output current. We will look at the waveforms. This is the supply voltage or the input voltage, which is AC. Now we are looking at the output voltage, that is V0. just tell me in which part my diode is forward biased. For forward biasing the diode, this anode voltage has to be greater than the cathode voltage. Here, my diode is forward biased. Here it is reverse biased because the anode voltage is getting negative in the negative cycle. Reverse bias. Here it is forward bias and then reverse bias. This goes on repeating in each and every cycle. You know the characteristics of diode. When it is forward biased, it conducts fully. When it is reverse biased, it is off. This is the positive cycle. It is forward biased. It conducts fully, meaning whatever input is there, that comes as it is. It is like a closed switch in the forward biased condition. So I get a same output, which is I will get the same input at the output. Now, when the diode is reverse biased, what happens? Diode acts as a open switch. There is no current flowing in the circuit, thereby my voltage is 0. V0 equal to I0 into R. Since I0 is 0, my V0 is 0. This is the single phase one pulse diode rectifier. This is uncontrolled rectifier. This is what? Uncontrolled rectifier. This is uncontrolled rectifier. Meaning what? If input is fixed, my output DC voltage is also fixed. If the input is fixed, the output also fixed. But in many applications, I require variable DC voltage, at the output. So I go to thyristor based or the SCR based converters. Those are called as controlled rectifiers. Whatever I have discussed here, it is very basic thing. Okay. Here, if the input is fixed, output is also fixed. But in most of the applications, I have to vary the output. So in those cases, we go to the controlled rectifiers. We will see one of them. We will see the controlled rectifiers. The variation is, instead of diode, I have put SCR or the thyristor. Now we will see the output voltage. The input is as usual, that is The input is as usual. That is what? Vs equal to Vm into sin omega t. This is the input. We are interested in the output. Now, again the same funda is applicable. We have to see when the thyristor is forward biased. We have already seen if it is a diode, it is forward biased in the positive cycle. The same thing applicable even for the thyristor. Similarly, it is reverse biased in the negative cycle, and this repeats for every other cycle. Now, this is a thyristor. If it is forward biased, we can trigger it. Okay, we can trigger it. We can make the thyristor to conduct when it is forward biased. Let us suppose say I gave the gate signal at some instant. Let us suppose say this is like omega t equal to alpha, and even in the second cycle I gave the triggering at omega t equal to alpha. Now we will see how the output looks. Okay. When I fire the SCR, when I give the gate signal, this SCR acts as a closed switch, meaning it is short. It connects output to the input. So my output voltage is same as the input voltage. So here I get the output. Now here the SCR is reverse biased. Obviously it acts as a open circuit. So output is not connected to the input. So the V0 value is 0. In this part, the thyristor is forward biased, but I have not triggered. So it acts as a open circuit. If it is open, the output is not connected to the input. Open means what? My current is 0. The voltage, which is I0 times R, that is also 0. So here also I get 0. So actually my output is a part of the input voltage. From alpha to pi, my output appears. Similarly, from 2 pi plus alpha to 3 pi, 2 pi plus alpha to 3 pi, my output appears. Now, if I vary the alpha, what happens? The waveform changes. Meaning, let us suppose if I make alpha somewhere here, what happens? My output will be coming from this instant to this instant to this instant. So I get more and more output voltage. Let us suppose I move alpha to the right side. Then what happens? Let us suppose I find this here at this point. So instead of getting this much output, I get small portion. Then what happens? My average output voltage is decreased. Now, we will see what is I0. We know for a resistive load, I0 equal to what? V0 by R. So I0 looks more or less similar. Waveform of I0 is similar to the V0, but its magnitude will change. This is the I0. This peak value is different from this peak value. Here the peak value is Vm. This is my peak value. Here the peak value is Vm by R. I0 is nothing but V0 by R. And I have to know the IS value also. That is the source current. Since this is a source, since this is a series circuit, my IS is always equal to I0. So the IS and the I0, both the waveforms are similar. Now observe one thing. Here I have taken Vs as the reference. Okay. The IS can start appearing from any instant. It start appearing from alpha. This alpha is variable. That is the triggering angle. So what I am doing is I am changing the phase angle between the start of input voltage and the start of input current. That is the phase control mechanism. I am changing the phase angle between the start of input voltage and the start of input current. This is what the phase control I am doing. Because of that, my output voltage, it is changing. Because of this, my output voltage, it is changing. So that is the main principle of this phase controlled rectifier. Now we will calculate the average output voltage. That is VDC or V0 DC. So how do we calculate V0 DC? We have to take the integration over one cycle. That is 1 by 2 pi integral V0 d omega t. This is from 0 to 2 pi. But actually the V0 is appearing from where to where? It is appearing from alpha to pi and elsewhere it is 0. So I take the limits from alpha to pi and Vm into sin omega t d omega t. So what we get? Vm by 2 pi into cos omega t. Limits are from alpha to pi. After simplification, I get Vm by 2 pi into 1 plus cos alpha. My V0 DC is what? Vm by 2 pi into 1 plus cos alpha. If I vary alpha, my output is also variable. If I vary alpha, my output also variable. If I increase alpha, what happens? My V0 value decreases. The same thing you can get it from the waveforms also. When you increase the alpha, the area that is appearing for the output voltage, it is decreasing. Thereby, my V0 DC also decreases. V0 DC also decreases. Alpha is variable from 0 to 180 degrees. Because in this duration, my thyristor is forward passed. So alpha I can vary from 0 to 180 degrees. V0 DC equal to Vm by pi for alpha equal to 0. This equal to Vm by 2 pi for alpha equal to 90 degrees. This equal to 0, 0 for alpha equal to 180 degrees. So if I increase the alpha value, what is happening to V naught DC? It is decreasing in its magnitude. So I can vary the output voltage by varying the firing angle. So this is the principle of phase control mechanism. The range of firing angle is firing angle is 0 less than or equal to alpha less than or equal to 180 degrees. This is the range of firing angle. Now I have calculated the V naught DC. And I have to find I naught DC also. I have to calculate the I naught DC. Always we calculate V naught DC for the first step. Next we calculate the I naught DC for the second step. Whether he has asked V naught DC or I naught DC, it doesn't matter. First you calculate the V naught DC. If V naught DC is asked, it is fine, you have got. But let us suppose you have to calculate I naught DC. Then also you calculate the V naught DC and then you calculate I naught DC. Since it is a resistive load, here it looks very simple. I naught DC is what? V naught DC by R. V naught DC by R. It is very simple. For the resistive load, it is very simple. For other loads, you follow the same procedure. There we will calculate I naught DC from the V naught DC. Now we calculate the V naught RMS. Why we have to calculate the RMS voltage or the RMS current? Sometimes what happens is like load consumes power for all harmonics. Like let us suppose I take the resistive load. It consumes power for all harmonics and DC component. So if I take the resultant of harmonics and the DC, I get RMS current or the RMS voltage. So for resistor, always I have to calculate the RMS current. Let us suppose if I have the battery, DC battery. In this case, I have to calculate I naught DC. I naught RMS, it has no meaning if my output is DC battery. For resistive load, I am interested in RMS values. It is RMS voltage or the RMS current. But for DC battery, I am interested in DC current. So depending upon the type of load, sometimes you have to calculate either the RMS voltage or the DC voltage. Since the load is resistive load, we will calculate the V0 RMS. V0 RMS. Now I have to calculate the V0 RMS. First I will calculate the V0 RMS square and then I will take the square root of that. This is what I have to take the integration over 1 period V0 square into d omega t. So what I get? 1 by 2 pi. The output is appearing from alpha to pi. Vm square sin square omega t into d omega t. Okay. What I get? Vm square by 2 pi integral alpha to pi sin square I write it as 1 minus cos 2 omega t by 2 into d omega t. Now I do the integration. After this, what I get? I get Vm square by 4 pi omega t minus sin 2 omega t by 2, limits of integration from alpha to pi. So I get Vm square by 4 pi minus alpha plus sin 2 alpha by 2. I am interested in V0 RMS. That equal to Vm by 2 root pi minus alpha plus sin 2 alpha by 2. This is what V0 RMS. If I want I0 RMS, it is V0 RMS by R. The same expression you divide by the resistance value. Then I get the I0 RMS. I have told you that for resistive load, the RMS voltage is important. If the load is having battery, constant voltage source, then we are interested in DC voltage. Okay. For these things, you refer to our chapter on basics. So there we have discussed like why for the constant voltage source we are interested in the DC values, either DC voltage or current. But for resistive load, why we are calculating the RMS voltage or the current. These things we have discussed in our chapter on basics. So those things you can refer. Now we will calculate the commutation time. Now we will calculate the commutation time. Commutation time it is the time for which my thyristor is reverse biased. It is reverse biased from pi to 2 pi. But this corresponds to omega Tc. Pi to 2 pi means the difference is what? Pi. Therefore, my computation time is pi by omega seconds. The computation is automatically provided by the supply itself, reverse of supply itself. Computation time is the time for which my SCR is reverse biased. It is reverse biased from pi to 2 pi, meaning for pi interval. Pi corresponds to omega Tc. But I am interested in Tc. So Tc is nothing but pi by omega seconds. Now we calculate the power factor. Power factor. It is defined on the AC side. So we calculate it as input power factor because input is AC. The basic principle we use is power delivered equal to power absorbed. What is power delivered? It is Vs, IS. These are the RMS parameters into cos pi equal to the power observed. The power observed in the load is what? V0 RMS into I0 RMS. This is RMS current and this is also RMS current. Since this is a series circuit, these two values are same. So what I get? Cos pi equal to V0 RMS divided by Vs. This Vs is again the RMS voltage. So what is V0 RMS? Vm by 2 root pi under root pi minus alpha plus sine 2 alpha by 2 divided by what is Vs? It is Vm by root 2. So after simplification what I get? I get 1 by 2 root pi into root pi minus alpha plus sine 2 alpha by 2. This is what the power factor, cos pi, or the input power factor. That is 1 by under root 2 pi into root pi minus alpha plus sine 2 alpha by 2. Now, the type of commutation. Type of commutation. Meaning how the commutation is happening. It is happening because of reversal of supply voltage. The supply is getting reversed. So what happens? It reverse biases the SCR and thereby it is turning up. So the commutation is natural. because of natural reversal of supply, the commutation is happening. So the type of commutation is natural commutation, or you can say line commutation, because the line voltage is getting reversed and then it is commutating my device. So it is either natural or the line commutation. Both means here it is same. Now we will see simple way of remembering the expression for V0 DC. V0 DC. What is the expression for V0 DC? For resistive load, Vm by 2 pi into 1 plus cos alpha. This is nothing but what? 1, since my pulse number is 1. And the maximum voltage that I have is Vm. Okay, divided by, I am having the 2 pi as my cycle period into cos alpha minus cos beta. Here beta is pi. So what I get? I get Vm by 2 pi into 1 plus cos alpha. So here, since it is a 1 pulse, I got multiplier as 1. If it is a 2 pulse, instead of 1, I get 2 here, 2 as the multiplier. If it is a 3 pulse, instead of 2, I get 3 as the multiplier. If it is a 6 pulse, I get, multiplier as 6 instead of 3. So in general, if my pulse number is n, so how can I write the V0 DC? N into the maximum voltage that I am getting divided by 2 pi into cos alpha minus cos beta. But here I have to add something, diode angle. This diode angle is 0. Diode angle is 0 in this case. Diode angle is 0 for n equal to 1, 2. It equal to 30 degrees for n equal to 3. That equal to 60 degrees for n equal to 6. So even if I vary the pulse number, I can generalize this formula. This is the most important formula. In most of the cases, I get the problems based on average voltage or the average current. 80 to 90% of the problems we get based on V0 DC. For this, we can use single expression. So this is the way to remember the formula. Again, I will repeat. How do we remember V0 DC? V0 DC is proportional to what? Number of pulses. If I have more number of pulses, I get the more output voltage. So V0 DC is proportional to N into V max. That is the maximum voltage that I am getting in the circuit. So that is also proportional to V0 DC. Divided by 2 pi. Because I am integrating the V0 for 2 pi duration into cos alpha plus diode angle minus cos beta. This alpha is what? Firing angle. Beta is extinction angle. extinction angle. So for resistive load, whatever we have discussed, this beta is nothing but pi, and also diode angle 0. I have told you because n is 1. This diode angle depends upon the n value. If n is 1 or 2, diode angle is 0. If n is 3, diode angle is 30 degrees. If n is 6, diode angle is 60 degrees. These all things we will cover when we go to the different pulse converters. But here I am giving you the general guidelines how to remember the expression for the average output voltage. There is nothing actually. It is more of logical. If you understand the logic, you can straight away write the formula for any pulse converter. Any pulse converter. Now we have a small observation. When alpha lies between 0 to 90 degrees, V naught max, the maximum instantaneous output voltage, maximum value of instantaneous output voltage, that is what? Vm. If alpha is less than 90, meaning it is 0 to 90 degrees, then my output voltage will be going through the peak value. So obviously maximum value of instantaneous output voltage, it is Vm. When alpha is in between 0 to 90 degrees, my output voltage looks like this, and this instantaneous output voltage, it goes through the peak value Vm. So my maximum value of instantaneous output voltage in this case is Vm. But when alpha is in between 90 to 180 degrees, what is V naught max? Observe here. Let us suppose that my firing angle is here somewhere. It is greater than 90. It is greater than 90 and less than 180. In that case, I get this part of output voltage. Only this part of output voltage. So my maximum instantaneous output voltage, it is not Vm. It is less than Vm. So what I get? I get Vm into sin alpha, because this value corresponds to what? Vm into sin alpha. So whatever sudden change in voltage I get, that itself becomes the peak voltage. So when alpha is in between 90 to 180, the maximum instantaneous output voltage that I get is Vm into sin alpha. So this is the important observation. Now we will see the expression for average output voltage. There we will link for some other things. We will see the expression for the average output voltage. There we will see some concepts. The expression for the output DC voltage we have seen N into V max divided by 2 pi into cos alpha. I have told you here I have to add something, that is diode angle minus cos beta. This is valid for any pulse number like n equal to 1, 2, 3 or 6. And also load can be anything. Load can be R or RL with freewheeling diode, or load can be RE or RLD or RLD with freewheeling diode. The moment when I have inductor, I can add the freewheeling diode. So when inductor comes, I can go for the one more case. Whatever expression I have written, it is valid up to this part only for the time being. This expression has to be modified little bit. to accommodate these three loads. When we go to RE or RLE loads, we will take care of this E in the load. When E comes, we have to add some expression. E into something. These things we will discuss in detail when we go to the other loads like RE, RLE or RLE with freewheeling diode. Generally in the textbooks, this formula is not given. What they do is, they take two assumptions. One is continuous conduction. Continuous conduction. And they give the expression in terms of sign function. These two things we have modified. This expression is valid for the continuous conduction or the discontinuous conduction, and also for any pulse converter and also for any load. So this is the most generic formula. This is not given anywhere. This we have modified. These things we will add when we go to the subsequent loads. If sign function is given, then it becomes little bit tough to remember. Cos terms are very easy to remember. I will explain this formula once again. V0 DC is equal to n into. When the pulse number increases, my V0 DC increases. So V0 DC has n as the direct multiplier, and also the Vmax. The higher the Vmax, my V0 DC value is higher. So Vmax directly comes as a multiplier. This 2 pi corresponds to the cycle time period. Okay. This part, it comes as a cos term, because in the integration I take the sine term and then I am doing the integration. Integration of sine is cos. That's why I get cos alpha. This is the firing angle. This is the angle from which my output starts. And this is the instant where the conduction extinguishes. This is the extinguishing angle. This is the extinguishing angle. This alpha corresponds to the time interval. This alpha corresponds to the time instant where my conduction starts. This beta corresponds to the time instant where my conduction stops. Okay, this is in my control. Firing angle I am giving to the circuit. So this is also known. This parameter, everything is known. Diode angle, this I have already discussed. This is 0 for n equal to 1 or 2, and this is 30 degrees for n equal to 3, and this becomes 60 degrees when n equal to 6. So this is depending upon n. The moment when we know the n, this value also known. This is known, this is known, this is known, this is known. Alpha, it is in our control. It is the firing angle. It is given by the quarter. It is given by assumed. So through gate signal we are giving. So alpha is in our control. Extinguishing angle, it depends on the load. This we have to identify from the problem. For the R case we have seen, beta is directly 180. If it is RL load, beta will be greater than 180. For RL load, generally beta is given in the problem. Whenever inductance is there in the load, beta value is specified. So in the problems, just we have to substitute these values. Only the problem comes when we are finding the beta. Beta we have to find out from the problem. In the R case, it is 180 degrees. RL load, beta is greater than 180. Beta is greater than 180 for RL load. typically when inductance is there in the load, beta value is specified because it is tough to find out it is tough to calculate the beta value for inductive loads because it is very rigorous equation. It is very tough to calculate beta. So for inductive loads, beta is given. And E, and also here we get some terms. These things we will discuss when we go to the RE load or RLE or RLE plus pre-limited. Wherever E is there in the load, there we discuss these things.